Here in item 2 we have a simply supported beam that has overhangs on either side, distributed load over a portion of the beam, and two different concentrated loads. We're asked to, if we were given the moment diagram or moment function, we want to then find our displacement equation. And how would we break up the beam or the mathematical model to do that? So we're going to start with the idea that G from moment curvature, we know that kappa equals m over EI, and that kappa is the second derivative of transverse displacement. And so anything that would break up E and I or M as a function along the length of the beam would then make us have to think about this in terms of beam segments. EI is constant, so therefore it's only things that would break up the moment. So as I take a look at that and say, well, alright, it turns out, of course, that the second derivative of the moment is equal to the distributed load. That, of course, comes from that the shear is associated with the load and that the moment is associated with the shear. So anything along the way that would break things up in terms of a nice simple mathematical function will create then different beam segments. And so what we have here is a point load that creates an immediate change in the shear, but we have a nice smooth transition until we get over to the reaction. So that's going to create the beginning and end of a beam segment, and that also coincides with the beginning of a distributed load, which as we flow along to point C, the point load creates another discontinuity, and so that begins and ends another segment, and so on and so forth. So we end up with 4 beam segments that in this case are entirely just associated with our discontinuities in our loading function or in the shear function created by the concentrated loads. We don't have applied moments, and we don't have changes or breaks in the slope or other things from a displacement standpoint going on. We just have these discontinuities, but that gets us there. Okay, now then we're asked to identify the displacement related boundary and continuity conditions. The boundary conditions are going to be that the displacement at B is equal to 0 and the displacement at D is equal to 0. That would be the roller and pin support that those two are associated with. The continuity conditions refer to these beam segments, and so our mathematical function, that is the transverse displacement, has got to have in these different segments some sort of continuity that's going across that particular location. So for instance, at x equal to b, or really x equal to 0, but at b, we end up with that our displacement from segment 1 must equal the displacement of segment 2, but also, because of the boundary conditions, happens to be equal to 0. The slopes from those two regions at x equal to b, or at that location, have to be equal to each other, not equal to 0, but they have to be equal to each other. At C, we would have something similar, that now that the displacement from the two equations from segment 2 and 3 must be equal to each other. Don't know what those are. Likewise, the slopes have to be equal across that mathematical interface, and we get a similar thing happening there at D, that our displacements have to be equal to each other and equal to 0, as well as the slopes coming from those two segments in their equations must be equal to each other. Again, don't know what they are. Right, so these bottom sets are the continuity conditions, and the top set was the boundary condition.